A free-electron laser is a type of laser whose lasing medium consists of very high-speed electrons moving freely through a magnetic structure, hence the term free electron. The free-electron laser is tunable and has the widest frequency range of any laser type, currently ranging in wavelength from microwaves through terahertz radiation and infrared, to the visible spectrum, ultraviolet, and X-ray. The term free-electron lasers was coined by John Maddy in 1976 at Stanford University. The work emanates from research done by Hans Motz and his co-workers, who built an undulator at Stanford in 1953, using the wiggler magnetic configuration, which is the heart of a free electron laser. Maddy used a 43 MeV electron beam and 5 meters long wiggler to amplify a signal. Beam creation. To create and fell, a beam of electrons is accelerated to almost the speed of light. The beam passes through an undulator, a side-to-side magnetic field produced by a periodic arrangement of magnets with alternating poles across the beam path. The direction of the beam is called the longitudinal direction, while the direction across the beam path is called transverse. This array of magnets is called an undulator or a wiggler, because it forces the electrons in the beam to wiggle transversely along a sinusoidal path about the axis of the undulator. The transverse acceleration of the electrons across this path results in the release of photons, which are monochromatic but still incoherent, because the electromagnetic waves from randomly distributed electrons interfere constructively and destructively in time, and the resulting radiation power scales linearly with the number of electrons. If an external laser is provided or if the synchrotron radiation becomes sufficiently strong, the transverse electric field of the radiation beam interacts with the transverse electron current created by the sinusoidal wiggling motion, causing some electrons to gain and others to lose energy to the optical field via the ponderomotive force. This energy modulation evolves into electron density modulations with a period of one optical wavelength. The electrons are thus clumped, called microbunches, separated by one optical wavelength along the axis. Whereas conventional undulators would cause the electrons to radiate independently, the radiation emitted by the bunched electrons are in phase, and the fields add together coherently. The fell radiation intensity grows, causing additional microbunching of the electrons, which continue to radiate in phase with each other. This process continues until the electrons are completely microbunched and the radiation reaches a saturated power several orders of magnitude higher than that of the undulator radiation. The wavelength of the radiation emitted can be readily tuned by adjusting the energy of the electron beam or the magnetic field strength of the undulators. Fells are relativistic machines. The wavelength of the emitted radiation is given by, or when the wiggler strength parameter k, discussed below, is small, whereas the undulator wavelength is the relativistic Lorentz factor, and the proportionality constant depends on the undulator geometry and is of the order of 1. This formula can be understood as a combination of two relativistic effects. Imagine you are sitting on an electron passing through the undulator. Due to Lorentz contraction, the undulator is shortened by a factor and the electron experiences much shorter undulator wavelength. However, the radiation emitted at this wavelength is observed in the laboratory frame of reference, and the relativistic Doppler effect brings the second factor to the above formula. Rigorous derivation from Maxwell's equations gives the divisor of 2 and the proportionality constant. In an X-ray fell, the typical undulator wavelength of 1 cm is transformed to X-ray wavelengths on the order of 1 nanometer by 2000, i.e., the electrons have to travel with the speed of 0.9999998 c. Wiggler strength parameter kk, a dimensionless parameter, tells the wiggler strength as the relationship between the length of a period and the radius of bend, whereas the bending radius is the applied magnetic field and the electron mass. Quantum effects. In most cases, the theory of classical electromagnetism adequately accounts for the behavior of free electron lasers. For sufficiently short wavelengths, quantum effects of electron recoil and shot noise may have to be considered. Large facilities required. Free electron lasers require the use of an electron accelerator with its associated shielding, as accelerated electrons can be a radiation hazard if not properly contained. These accelerators are typically powered by klystrons, which require a high-voltage supply. The electron beam must be maintained in a vacuum, which requires the use of numerous vacuum pumps along the beam path. While this equipment is bulky and expensive, free electron lasers can achieve very high peak powers, and the tunability of fells makes them highly desirable in many disciplines, including chemistry, structure determination of molecules in biology, medical diagnosis, and non-destructive testing. X-ray laser without mirrors. The lack of immaterial to make mirrors that can reflect extreme ultraviolet and X-rays means that fells at these frequencies cannot use a resonant cavity like other lasers, which reflects the radiation, so it makes multiple passes through the undulator. Consequently, in an X-ray fell, the output beam is produced by a single pass of radiation through the undulator. There must be enough amplification over a single pass to produce an adequately bright beam. X-ray free electron lasers use long undulators. The underlying principle of the intense pulses from the X-ray laser lies in the principle of self-amplified spontaneous emission, which leads to the micro-bunching. Initially, all electrons are distributed evenly and they emit incoherent spontaneous radiation only. Through the interaction of this radiation and the electrons' oscillations, they drift into micro-bunches separated by a distance equal to one radiation wavelength. Through this interaction, all electrons begin emitting coherent radiation in phase. All emitted radiation can reinforce itself perfectly, whereby wave crests and wave troughs are always superimposed on one another in the best possible way. This results in an exponential increase of emitted radiation power, leading to high beam intensities and laser-like properties. Examples of facilities operating on the SASE fell principle include the free electron laser in Hamburg, the LINAC coherent light source at the SLAC National Accelerator Laboratory, the European X-ray free electron laser in Hamburg, the Spring 8 compact SASE source, the Swiss FEL at the Paul Scherrer Institute, and, as of 2011, the SACLA at the RIKEN Harima Institute in Japan. Self-seeding. One problem with SASE fells is the lack of temporal coherence due to a noisy startup process. To avoid this, one can seed and fell with a laser tuned to the resonance of the fell. Such a temporally coherent seed can be produced by more conventional means, such as by high harmonic generation using an optical laser pulse. This results in coherent amplification of the input signal. In effect, the output laser quality is characterized by the seed. While HHG seeds are available at wavelengths down to the extreme ultraviolet, seeding is not feasible at X-ray wavelengths due to the lack of conventional X-ray lasers. In late 2010, in Italy, the seeded fell source Fermi-Teletra started commissioning at the synchrotron Trieste laboratory. Fermi-Teletra is a single-pass fell user facility covering the wavelength range from 100 nanometers to 10 nanometers, located next to the third-generation synchrotron radiation facility Elettra in Trieste, Italy. The advent of femtosecond lasers has revolutionized many areas of science, from solid-state physics to biology. In 2012, scientists working on the LCLS overcame the seeding limitation for X-ray wavelengths by self-seeding the laser with its own beam after being filtered through a diamond monochromator. The resulting intensity and monochromaticity of the beam were unprecedented and allowed new experiments to be conducted involving manipulating atoms and imaging molecules. Other labs around the world are incorporating the technique into their equipment. Applications: medical surgery. Research by Glenn Edwards and colleagues at Vanderbilt University's Fell Center in 1994 found that soft tissues including skin, cornea, and brain tissue could be cut, or ablated, using infrared Fell wavelengths around 6.45 micrometers with minimal collateral damage to adjacent tissue. This led to surgeries on humans, the first ever using a free-electron laser. Starting in 1999, Copland and Conrad performed 3 surgeries in which they resected meningioma brain tumors. Beginning in 2000, Hughes and Morn performed 5 surgeries that cut a window in the sheath of the optic nerve, to test the efficacy for optic nerve sheath fenestration. These 8 surgeries produced results consistent with the standard of care and with the added benefit of minimal collateral damage. A review of Fells for medical uses is given in the first edition of Tunable Laser Applications. Fat removal. Several small clinical lasers tunable in the 6 to 7 micrometer range with pulse structure and energy to give minimal collateral damage in soft tissue were created. At Vanderbilt, there exists a Raman-shifted system pumped by an Alexandrite laser. Rox Anderson proposed the medical application of the free electron laser in melting fats without harming the overlying skin. At infrared wavelengths, water in tissue was heated by the laser, but at wavelengths corresponding to 915, 1210 and 1720 nanometers. Subsurface lipids were differentially heated more strongly than water. The possible applications of this selective photothermolysis include the selective destruction of sebum lipids to treat acne, as well as targeting other lipids associated with cellulite and body fat, as well as fatty plaques that form in arteries, which can help treat atherosclerosis and heart disease. Biology. Exceptionally bright and fast X-rays can image proteins using a sheet just 1 molecule thick. This technique allows first-time imaging of proteins that do not stack in a way that allows imaging by conventional techniques. 25% of the total number of proteins. Resolutions of 0.8 nanometers have been achieved with pulse durations of 30 femtoseconds. To get a clear view, resolution of 0.1–0.3 nanometers is required. The short pulse durations prevented the lasers from destroying the molecules. The bright, fast X-rays were produced at the LINAC coherent light source at SLAC. As of 2014, LCLS was the world's most powerful X-ray Fell. Military Fell technology is being evaluated by the U.S. Navy as a candidate for an anti-aircraft and missile-directed energy weapon. The Thomas Jefferson National Accelerator Facility's Fell has demonstrated over 14 kilowatts power output. Compact multi-megawatt class Fell weapons are undergoing research. On June 9, 2009, the Office of Naval Research announced it had awarded Raytheon a contract to develop a 100 kilowatts experimental Fell. On March 18, 2010, Boeing Directed Energy Systems announced the completion of an initial design for U.S. naval use. A prototype Fell system was demonstrated, with a full-power prototype scheduled by 2018.